for Lambda class. In this episode, we're going to discuss metric spaces, Hamming distance, and we'll talk about a little bit about coding theory. Um, we need to start by explaining what we mean by distance, uh, mathematical distance. Okay, so what we need to do, we need to quantify how far apart things are. So let's start with a base set called M. Let's start with a non-empty set M. So we need to define a distance on M. A distance on M is a function D that takes two elements of M and assigns a real number such that, okay, we're gonna ask this function to fulfill certain requirements. Well, first of all, the distance between any two elements of D should be a non-negative number. Distances are going to be either 0 or a positive number. Secondly, well, the distance between any 2 points is unchanged um, when we take it from x to y or from y to x. Distance doesn't have an orientation for us. Okay, this is some sort of symmetry or commutativity um, requirement. Okay, next we're gonna say that the distance between 2 points is 0 if and only if the points are actually the same, right? So two different points have a positive distance between them. And fourth, which is the triangle inequality, distance between x and y is bounded above by the distance of x and c plus the distance of c and y. This is what we call the triangle inequality. Okay, so whenever we find a function on a non-empty set M that satisfies these requirements, we call it a distance. Okay, and we will call the pair MD a metric space. Okay, in metric spaces, we are starting to think of geometry in terms of points. Okay, points being close or being far away, or having any property regarding distance. Okay, so working with a metric space is working with a non-empty set and a function that satisfies all these four requirements. Okay, so let's put some examples to all this. So let's start with an example. Example 1. Let's take the Euclidean plane, R2, right? R2, we can draw it like this. It has a x-axis, a y-axis, and points. Say you have a point here, call it P, and a point Q. These points have coordinates, right? P will have an an x coordinate and a y coordinate, and Q will have an x coordinate and a y coordinate, right? So how do we measure the distance between P and Q? What's going to be the distance between these points? Well, it's going to be the length of this line, right? And how do we compute the length of that line? Well, using the theorem of Pythagoras, right? So we form a triangle, and we'll say that this distance is actually the length of the hypotenuse, right? So that's the square root of this leg, which can be computed as x2 minus x1 squared plus this other leg squared. So we have here is y2 minus y1 squared. Okay, and that's the distance between those 2 points. We need to check that this function d actually satisfies everything that we ask. Okay, distance between P and Q is always going to be a non-negative number since it's a square root of a positive number. It is obviously commutative because the square eats up all the signs. And the properties 3, that follows from the properties of the square root, and the triangle inequality is actually the triangle inequality. Okay, so in this case we have a very familiar distance. This is a very familiar notion for us to measure distance between points. Okay, let's go to a different example. Let's try example 2. Now we're going to take the integers as our set. We're going to take a look at the integers as a subset of the real numbers. So if you draw a real line here, it's going to be R, and you select the position for 0, then you have 1, 2, 3, well, here we have -1, -2, -3, etc. This is the set of the integers. We're gonna define a metric on M, on C, right? Now the distance between two integers, say M and N, is gonna be actually the absolute value of the subtraction, right? It's the absolute value of the difference between them. This gives, again, a function that satisfies those 4 requirements. Obviously, absolute value is a non-negative result. It is symmetric because the absolute value eats up the signs, and obviously satisfies triangle inequality. And this third property, different integers have positive distance between them, right? For more maybe complex example 3, we can take a look at the set of continuous functions in a compact interval, right? This is the set of functions that are continuous. Okay, so one of these functions has a graph, right? So this is 0, and this is 1, and say a function that satisfies belonging to this place will be a function that has a graph that goes something like that. Then if we call this function f, then we can find another function called, say, g, and maybe we can draw a different function, h. So continuous functions on a compact interval. The interval goes from 0 to 1 and contains the endpoints, right? And for instance, a distance function that we can define here is going to be calculated as the maximum of the absolute value of the difference between them. Well, this is, first of all, this is well defined. By Weierstrass theorem. This difference, when you take the absolute value, ends up being a continuous function, and a continuous function always attains its maximum when it's defined on a compact interval, right? So these are very different sets and very different distance functions, but all satisfy this axiomatic. Okay, all these functions satisfy these properties. So we can talk about all these examples with the same language. We have a theory that's robust enough to talk about all these three very different scenarios, right? And some important objects. Single most important object in metric space theory is the notion of a ball. Bx epsilon is what we call the ball around x of a radius epsilon greater than 0. And this is described as the set of elements in M such that the distance to x is less than epsilon. Okay, so this is a fundamental object in this theory. Obviously, in each example, balls look different. How do balls look? Well, when you take the Euclidean plane with Euclidean distance, now say you want to take a look at the ball at a center at 0 of radius epsilon. This is all the p's in R2 such that the distance between 0 and p is less than epsilon. If you write it down, it's the set of p1 squared plus p2 squared less than epsilon squared. So if you take a look, this is just a regular circle of radius epsilon, right? So if this is epsilon minus epsilon, 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 and minus epsilon, You have the circumference limiting the actual ball, right? All this is the ball that we're talking about. It's the ball radius epsilon around 0, right? If we change the metric, which we can do, balls are going to look different. What if we change the distance function? Well, then balls are going to look differently. Say that we change the distance, and now we propose, say, what can we do? Okay, maybe can put it like this. Okay, let's try P1 minus Q1 plus P2 minus Q2. Okay, so now balls are going to be decided by this new distance function. Okay, so in this case, you're going to take a look at how the distance is going to turn out. What's going to be the ball center at 0 of radius epsilon? Well, it's not going to be something extremely different, but it's going to look quite different. Now, you have to think of this polygon, and the actual ball is going to be everything that's contained inside. So this is the ball that we're talking about. If you change the distance, the shape of the ball changes. Okay, so we have lots of freedom in terms of how to model things. Okay, metric spaces are really flexible and allow lots of other structures to sneak into the picture. And why am I saying this? Because here we have numbers, we have subtraction of numbers, we are applying functions to numbers, so we are doing not only arithmetic and algebraic operations, but we're actually letting functions appear in this context. Okay, so both are really important. Let's give a second example. Let's take a look at z and the distance that we talked about as the absolute value of the difference. Okay, so what's going to be, say, the ball centered at 2 of radius 3. This consists of all the integers such that the distance to number 2 is less than 3. Oh, if you take a look at the real numbers, this is a real line, and we pick a place for 0, then you have 1, 2, 3. Let me correct this a little bit. I have 4, 5, and say minus 1 over here. So this is a real line. Then what is this? This is the set of integers that have distance less than 3. So the center of the ball is here. This is the center of the ball. Number 3, number 4, number 1, and number 0, they all have distance less than 3. You know, this has distance 1, this has distance 2. So when you take a look at this, what you get is this interval, right? You can think of it as an open interval in R, but when you go more specific, this is just a subset of the integers. It's 0, 1, 2, 3, and 4. So this is what that ball looks like. Balls in this context for this set and this metric is actually a finite set. Okay, so this is what this ball looks like. Obviously, when the spaces have more complicated underlying sets, balls are going to look different as well. Okay, so balls are important. They are a foundational object in this theory, and they allow many other concepts to appear. Okay, so we'll start giving some definitions. Bounded sets. Let MD be a metric space we'll say that a subset A is a bounded set if A is a subset of a ball for certain, let's put M, for certain M in the metric space and epsilon greater than 0. So a set is bounded if it can be if it can fit inside a ball, right? Examples abound, and not every set is bounded. Okay, so observations. First of all, let's take an example 1. Let's take the unit circle. In R2, okay? X and Y. So the unit circle, let's call it S1 for historical reasons. Well, this is a bounded set because it can fit inside a ball. Can fit inside some ball of the space. This is a subset of a ball center at 0 of radius, say 2. So since we found a ball center at some point in the space with some positive radius and it contains S1, then S1 needs to be a bounded set. Okay. Observation. S1 is infinite. It has infinite many points and is bounded. Let's take a different example. Um, a a line in R2. What happens with a line in R2? Say you pick the line y equals to x. Then this set is not bounded, okay? Because for any ball that we choose, say center at 0, there are points of the line that lie outside, okay? Call this line L. L is not contained in any ball of radius epsilon. If we want to show that and maybe take a look at a different definition of being bounded, we need to exhibit a point that is farther than epsilon to 0. Say epsilon plus 1 belongs to L and is not in the ball. Right? So we have an infinite set that is bounded in the Euclidean plane, and we have an infinite set that is not bounded. So being infinite and being bounded are different things. Observation, alternative definition. We're happy with this. We're happy with this. So let's talk about a third thing. Let A be a subset of M, a finite set. So imagine that this is your ambient space and you have your set A. Consists of A1, A2, A3, and A4. Okay? So some things happen with A. Well, first of all, A is going to be bounded. If a set is finite, then it is automatically bounded. How do we show that? Okay, let's take epsilon to be greater than the maximum of the distances between the elements of A. That is, we measure all these distances and we take the bigger one. Okay? And then A is going to be included in that ball for some A sub I. So if A is a finite set, then it is a bounded set. Okay, we can say if you want, we can fix one of the elements as the center of the ball, then take a look at the distances and then take a radius which is bigger than the maximum of the distances. And then we're covered, okay? Then we're done. So if a set is finite, then it's bounded. Okay. And more importantly, what we have now is that A is a discrete set. And what do we mean by discrete? Well, this means that around each point there is a ball, maybe different in each case, different radius, say purple one, and now this one. Around each of its points, we can find a ball that contains just its center. That means that every point in A is an isolated point. This is A consists of isolated points. Definition: B belonging to A is an isolated point if there exists a radius epsilon such that the ball center at B of radius epsilon, when you intersect with A, gives you just B. This ball only contains one element of A, that is B. So this is the case for finite sets. Okay, finite sets are bounded, and finite sets consist of isolated points. Okay, so these are two important things. Especially, special case comes when the metric space is a finite itself. Then it's bounded metric space. Consisting of isolated points. Okay, so distances allow us to think of points as lying somewhere and having distance from one another. Okay, and this is a very weak idea, but at the same time it will allow us to do geometry in a way that's kind of more or less what we imagine geometry will have to look like. The good thing about this language is that it allows many different examples. So situations that are apparently way different can be seen in a common way with this framework of metric spaces. And we're going to talk about a little bit about a very important case for us, which are discrete metric spaces, and we're going to find something that's called the Hamming distance. And we'll talk about a little bit about coding theory. Okay, so let sigma be a finite set. This, in the cryptography jargon, is called the alphabet. And let's suppose that sigma has q elements. Okay. Um, we're going to define a metric in the Cartesian product, sigma to the n, which is sigma Cartesian, sigma Cartesian, sigma taken n times. This is the Cartesian product of sigma with itself n times. These are the order n tuples. Okay, these are going to be vectors of n slots, and its entries are elements of sigma. N is called, in the jargon again, the block length. Okay, so it's simply vectors that all the entries are elements of sigma, right? And we need to define a distance here. And we're going to define the Hamming distance. So let x be a vector and let y be another vector, both in sigma to the n. So we will define the, we'll use the capital sigma. We'll define the Hamming distance between x and y as the number of different entries in these two vectors. The number of places in which they differ. Mathematically, this can be written as the sum of an indicator function. This will count the number of slots in which x and y differ. Okay, so this is what we call the Hamming distance. Then we have the relative Hamming distance, which is simply the Hamming distance divided by the block length. This gives a relative version of the distance, okay? And these things are used in coding theory very, very much. So to fix ideas, let's use the alphabet 0, 1, 2, 3, and 4. This is actually isomorphic to C5. It's a finite field. When we consider the operations, arithmetic operations on it. And let's take a block length of, take n equal to 3. So this is simply vectors of 3 slots, x1, x2, and x3, such that each of the entries is a number between 0 and 4, integers, right? And so let's calculate for x, say 2, 2, and 1, and y equals to 1, 2, and 4. This is simply Hamming distance between these two guys. is simply counting how many times they're different. First slot, different. That gives distance at least 1. The second slot is the same, but the third slot is different again. So if we count how many times they are different, have this and this, which are different. So they have Hamming distance of 2. Simple as that. Now let's make some observations. Some observations. 1, sigma to the n is a finite set. So it is bounded and discrete. Second of all, distance between any 2 points of sigma to the n is actually a non-negative integer. That is, if x and y are different, then their distance is greater or equal to 1, right? And this will come handy to have some questions about what can we say with this set. So let's introduce the notion of a code. Definition: a subset C in sigma to the n is a code. Its elements are code words. So this is cryptographic jargon for a subset, okay? So we need to think of codes as points. In sigma to the n. Of course, in technical applications, n will be big. Q, which is the length of the alphabet, will be big, and C will be big. But for all practical purposes, we can think of a code as some points in sigma to the n. One thing that we can define is the minimum distance of a code. That is, if we have this code, say with C1, C2, C3, and C4, what we can do is we can measure distance between every pair of its elements and then take the minimum. This is well defined since C is finite. So the distance of a code is the minimum for C different from C prime of the distance between C and C prime. We call this minimum V. That means that any 2 code words are at least D apart. Any 2 code words are at least D apart. And also means that any ball with epsilon less than the floor of D minus 1 over 2 isolates C from the rest of the code. Again, if we take this picture of sigma to the n, and we have this picture, then we know that balls that have a radius smaller than d minus 1 over 2 actually isolate all the points. All these balls have the same, all these balls have radius d minus 1 over 2. And they isolate each code word. C1, C2, C3, and C4. So that's the distance of a code. That's the minimum of the distance between any two code words. And this allows us to cover the code with finitely many disjoint balls. They are all disjoint. Okay. For the time being, these are many definitions, but they're not complicated. And up to here, sigma was just a finite set. We could have considered A, B, C, the English alphabet, for instance. That would be an option. Another option would have been just an alphabet with 0 and 1. We could have considered an alphabet consisting of a triangle, 1, 2, and the letter D. Just a finite set. From now on, we're going to concentrate now on sigma will be a finite field. Of Q elements. And we're going to concentrate in this example because we need to talk about the way these balls are. Okay, so let's take a look at the ball center at 0. Let's explore the ball centered at 0. Right, the ball center at 0 of radius epsilon consists of all the elements of sigma to the n such that its Hamming distance with 0 is less than epsilon. Okay, and what does this mean? It has less than epsilon places which with non-zero entries. Right? Sometimes this is called the height of M. The height of M is simply the distance between 0 and M. So the ball center at 0 of radius epsilon consists of all the points in sigma to the n which have height less than epsilon. All right. For example, let's take sigma, which is the alphabet of 0 and 1, which is simply finite field set 2. Let's take block length 4. Okay, so we're dealing with sigma to the 4th. These are vectors with 4 entries, each of which is in set 2. Okay, so what is the ball centered at 0 of radius 3? It consists of all the elements of sigma to the 4 such that their height is less than 3. So this can be thought of the ones that have height 0 with the ones that have height 1 and the ones that have height 2. Okay, so these are the elements of sigma to the 4th which have height 0. The only element of height 0 is actually 0 itself. Has no entry different from 0. Okay, what about the elements of height 1? The elements of height 1 are all the vectors in sigma to the n to the 4th which have exactly one element which is non-zero. In this case, since the alphabet has only 2 letters, we only have this 4 elements, right? And what about those of height 2? Consists of the vectors of sigma to the 4th which have height 2. That is, they have only 2 spots in which they have entries different from 0. So we have a priori this guy's over here, and then this one, and then finally this one over here. Of course, so all of this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the ball centered at 0 of height 3 has 11 elements. Okay, this alphabet is a very small alphabet, 0 and 1, and the block length is 4. Okay, here Q equals 2 and N equals 4, right? And we have seen that we have written this ball as a union of disjoint sets. And we will see that the number of elements in this ball is actually the sum of the number of elements in the set of height I. 1, 2, 3. Right, so balls have the ball center at 0 have this bunch of other elements of sigma to the 4th. This is known as the volume of the ball. And in general, we can find a formula for the volume of the ball in sigma to the n when the alphabet has size q, which is basically a counting argument, right? So the volume of the ball center at 0 and radius epsilon will be simply a counting argument. We have ones of height 0, which is only 0, and then you just need to know how many different elements each of this one has, right? So first of all, for the ones of height 1, you need to choose a place in which to put all the other q minus 1 elements of the alphabet, q minus 1 non-zero elements. So n choose 1, this chooses a place to put q minus 1 options to the n. And you check this is correct. Q minus 1 to the q minus 1. That's it. Now we need to think of the ones of height 2. Now we need to choose two places. So we're going to add n choose 2, and now we're going to fill in with the q minus 1 remaining elements of the alphabet, 1 in each space. So this is 2. Obviously, this will go on to n to epsilon minus 1, q minus 1, and epsilon minus 1. Okay, so this formula actually gives the volume when the alphabet has size q. One of trivial observation that the distance between x and y is at most the block length. If the vectors have n slots, at most they differ in all places. The distance is at most n, which in turn gives that the height of an element is bounded by n. Okay, this is trivial observation 1. Second, typically epsilon is an integer between 1 and n. All right, so this will give us some idea of what to expect when we have an epsilon over there, right? For epsilon in n. All right, and now that we have that we know the volume of the ball center at 0, we give a non-trivial observation that the volume of the ball centered at 0 radius epsilon is actually the volume of any ball. Okay, so this is a good thing to think of. Think of it for a bit. Think about it for a bit. Okay, and to finish this video, we're gonna introduce something that's known as the Hamming bound. Which can be thought of as a very simple thing in terms of this picture. So say you have sigma to the n, and you have your code. Code C with distance d. That means that balls of radius d minus 1 over 2 are disjoint. And suppose that Q has is an alphabet of length Q. So the idea is, since sigma Tn is finite, the size of C can't be too big. That is, all the balls need to fit so there is a trade-off between the minimal distance and how many balls we have. Why? Because the balls had volume. All the balls need to fit inside sigma to the n. And how do we express that? Since all the balls have the same volume, the fact that all the balls need to fit is explained by, well, the volume of a ball centered at 0 with this radius times the number of elements in the code needs to be less than or equal to the number of elements in sigma to the n. So this bound is known as the Hamming bound. Or at least this is a initial version of the Hamming bound. All the concept behind this is the balls need to fit. And now there's a relation that will help us. This is actually sigma to the n, and this is q to the n. Taking q base logarithms, we have the logarithm base q of the size of C plus the logarithm base q of the volume of the ball centered at 0 and radius d minus 1 over 2. This needs to be less than or equal to n. Okay. So let's divide by n everywhere. Okay, and let's do some passage of terms. Well, first of all, we have the logarithm base q of the size of C over n. This needs to be equal or less than 1 minus the logarithm base q of the volume, d minus 1 over 2 over n. Now, this looks more like it. So if you take a look at this side, this depends on the. So the distance controls the right-hand side. Distance controls the right-hand side. And now we need to make sense of this expression over here. Is this. How we make sense of this? And this is not a very complicated idea. This has to do with the expressive power of our code. What can we say with this code? Well, we have the number of elements of C, code words, what messages can we encode? More specifically, what is the length? What is the length of the messages that C is able to encode? Well, this is a crucial question. What is the length of the messages that C is able to encode? Since our alphabet is sigma, then assigning a letter to each of the letters of the message, then what we have is this relation. Okay, and remember that Q is the number of elements on sigma, that we have is this. So taking Q-based logarithms, you have that K is the log base Q of the size of C. So when we ask what is the length of the messages that C is able to encode, we're asking which K do we have. So K is what we call the message length. So the Hamming bound is actually a trade-off between the message length divided by n and the distance. Message length divided by n is bounded above but 1 minus the volume of a ball, since we're at 0, this radius divided by n. This is a trade-off between this quantity, which is called the rate of the code, which is the message length between divided by the block length, and the distance. The rate measures the actual message and the size of the whole table that we're transmitting. Okay, how much redundancy the table of numbers has. And at the same time, the distance measures the ability of the code of actually detecting errors when we send the message. We're going to return to this in a future video, but we need to understand that the Hamming bound is simply trying to make every ball fit in the same space. Okay, this is an amazing topic. This is something that is very, very interesting and it's very useful. And we are going to see how polynomials enter this discussion in a future video. Okay, polynomials and coding theory are the base to Starks. Okay, the rate of the code and the distance of the code and all things zero knowledge, when expressed in terms of polynomials, make use of all these tools. All right. So we'll end this video for now, and we'll see you in the next one. Goodbye.